Morning all. Today I'll be presenting this talk titled Project Amiga Properties of the Photoionized Gas in M31 CGM. Over the past decade, significant leaps in characterization of the halos of low redshift galaxies have led us to the understanding that a significant fraction of the halos of these low redshift galaxies harbor photoionized gas at temperatures between 10 to the 4 to 10 to the 5 Kelvin. And several of these empirical studies also show that this photoionized gas is highly inhomogeneous, as evidenced by large metallicity variations that we see across kinematically distinct components within a single sight line tracing a halo. While we are interested in understanding this interplay of inflows, outflows, satellite halos, recycled accretion, as evidenced by this large variation in metallicity, inherent challenge that we contend with is that of the low surface density of UV bright quasars. Although useful when characterizing large ensembles of galaxies, a single sightline per galaxy would limit our understanding of the physical process playing out in galaxies. So, what we really want is several tens of sightlines probing the CGM of a single galaxy. This is precisely what is made possible with Project Amiga, which is a survey of several tens of sightlines probing the CGM of M31 all the way from 10 kiloparsec to 570 kiloparsec. The aim of this project is to map how the metals are distributed both in radius and in azimuth. Furthermore, experiments of this kind can help inform simulations, as such experiments control not only for differences in galaxy inclinations, sizes and star formation histories. So, this serves as an ideal test bed for simulations and for the recipes that go into them. Amiga stands for absorption maps in the CGM of in the gas of Andromeda, and this has been conducted thanks to two successful HST proposals. One, cycle 25, where 18 new QSO observations coupled with 25 archival observations gave us information on ions of silicon 2, silicon 3, silicon 4, carbon 2, carbon 4 and oxygen 6, and many more interesting results are published in this work, Lerner et al. 2020. Then a follow-up of this work was to understand how the inner CGM of M31 is linked to the outer CGM. And to do that, 12 new QSO targets were proposed for and secured, probing impact parameters between 10 to 75 kpc. So, on this physical map, the inner sightlines are shown in red and the outer ones in blue. For context, this is 300 kiloparsec, that is the virial radius of M31. So, for this work I have analyzed the absorption towards these inner sightlines, and I will be talking about these results in tandem with those of the outer sightlines from Lerner et al. 2020. So, here is an example of the absorption that we see along one of the inner sightlines. It shows multi-component and multi-phase absorption. This is a sightline at a distance of about 12 kpc from M31, quite close. And as we can see, we see multi-component absorption seen in several components and in multiple phases. We see absorption in low ions of carbon 2, silicon 2, in intermediate ions of silicon 3, silicon 4 and also high ions of carbon 4. Now, to search for absorption associated with M31, which we are interested in, we look for absorption within a velocity range of -600 to -150. This velocity range is set by the fact that below the maximal negative velocities that we see in the rotation curve of M31 are about -600, and beyond -150 we start to probe Milky Way absorption. In addition to contending with absorption associated with Milky Way, the other effect that we need to remove is that of contamination from high redshift absorbers. In the case of when we have access to multiple transitions of a single ion like silicon 2, we are able to do this by comparing apparent optical density profiles to identify presence of any contamination or saturation. That is one thing we need to contend with. In addition, because of the proximity of this sightline to the Magellanic stream, we also account for potential contamination from MS along certain components for sightlines with certain MS longitudes. So, with the contamination effects taken care of, these are the results. The plot on the left shows column densities as a function of impact parameter normalized by the virial radius, sorted from low ions to the high ions. As we see, the low ions up till the high ions show a general trend of decline in the column densities as we go outward. The decline in C4 and O6 is not as remarkable as seen in these lower ions. And also to note is that this is the virial radius. Beyond that, as we can see, the CGM is quite extended. We see absorption well beyond the virial radius of M31. The upper limits are shown as lightly shaded data points, and lower limits points with upward pointing arrows. On the right is the azimuthal distribution of column densities in C2, Si3 and C4. As we saw there, the strongest columns are seen closer in and they fall as we go outward, and we do not see any evidence of azimuthal dependence. That is the that is the major axis, that is the minor axis, and this is the major axis, and we do not see any preferential existence of columns along either of these or any certain angle. So, with the column densities ascertained, we can now go ahead and determine the metal mass of the cool photoionized CGM without resorting to ionization modeling, because we have access to the bulk of the gas that is contained within this these ions are known to trace bulk of the cool photoionized gas. So, we have access to total silicon column density plotted as a function of R. Clearly, what we see is that there is a sharp decline in the column densities within the inner region from about 10 kpc to about 50 kpc, and beyond that the decline is gradual. So, this motivates the choice of our functional forms. We fit a hyperbolic function as well as an exponential function, and we integrate this equation between 10 to 300 kpc, arriving at a value of about 4 times 10 to the 7 mson. For context, if we do not include these inner sightlines, the mass is about half. So, now the important thing is these inner data points are limits, they are lower limits. The reason is that these are saturations seen in silicon 3. So, we need to get stringent constraints on these fits. How can we do that? One approach is to take recourse to ionization modeling. So, here is where we have done some ionization modeling to get hold of the column densities that of silicon 3. Now, this modeling is briefly how this modeling works is that we do not measure the column densities and use them as inputs for our cloudy models. Rather, we input the entire available gamut of transitions from low to high ions and allow the algorithm to determine the number of components in the various phases, and then we summarize the inferred properties of the gas in these parameters: metallicity, density, neutral hydrogen column density, temperature, size and non-thermal broadening parameter. I will focus on the properties of one particular component, one at minus 400 kilometers per second. You see strong absorption in neutral oxygen, and to bring your attention to that component, that is this component, quite constrained in metallicity with a metallicity of about 110 solar. Now, you might ask, this is well constrained even without access to H1. How is that possible? It is likely happening because O1 is known to be a good tracer of the neutral component of the CGM, that is H1, and hence we are arriving at good constraints on the metallicity of that particular component. You will also notice that the other components show uncertainties up to 1 dex and even higher, where we do not have access to O1. where O1 is a non-detection. Now, although we don't have access to H1 in absorption, we have access to H1 in emission. And for this particular sight line towards Wiki 29, we see H1 emission that is quite consistent with absorption in O1. And the H1 estimate that we get from there is 19.7. That yields a metallicity that is quite close to minus 1.2 that we infer from there. So, looks like O1 indeed is a good tracer of the neutral component of the CGM. So, our main purpose of doing this ionization modeling was to determine the amount of saturation that may be present in silicon 3. Here I am showing how our modeling is able to do with ascertaining that level. With silicon 2 and silicon 4, we have good agreement. In all the cases, silicon 2 and silicon 4 agree well, both with AOD approach and our ionization modeling. This is a lower limit which could still be consistent. This is a lower limit which could still be consistent. This is an upper limit which could still be consistent, and silicon 4 is all consistent within uncertainties. Importantly, with silicon 3, we see that we need some corrections to be done. That is, the model predictions are higher. It is expected because silicon 3 is saturated, and how much higher is what is told by the models. For sight lines that are farther away, greater than 100 kiloparsec, we need corrections from 0.1 to about 0.5 dex. For sight lines that are closer in, we need even higher corrections, almost up to 0.8 dex. So, with that, I will leave the conclusion slide up and take any questions.
We have time for one or two quick questions. Anybody have a question or a comment about this? Alyssa, please.
Could you go back to the slide that had the H1 spectrum on it?
Yeah.
Wait, that one, yeah. It looks like there's a velocity offset between the H1 and the other things, and I'm just curious what your reason, what your thinking is on that.
One, this is very slight, and two, there could be offsets with cost alignments up to 15 to 20 kilometers per second.
I'm sorry, I couldn't hear the second thing because the noise is low.
Yeah, there could be misalignments in the cost wavelength solution of up to 15 to 20.
Really? Oh, okay.
Yeah, but yes, this, yeah.
Okay, if Manami could come up and start to get set up, please.
Yeah.
Please.
I just wanted to add a comment to that. Is this the one that's 12 kiloparsecs? So it's
Yes.
So I think part of it could be beam smearing from M31's rotation curve. It's quite a large beam, so you're picking up things closer to the systemic velocity.
Thank you.
Okay, any other questions or comments for Samir? Okay, let's thank the speaker. Oh, one more, sorry, you got one more question. Sorry, I didn't hear it, please, go ahead.
Sir, on the topic of velocities, have you mapped the relative velocities of all the ions in all the different locations and tried to fit a kinematic model?
Yes, so that is what the aim of this forward modeling is that I need to put it in a more form of a plot, but that is work in progress.
Thank you.
Okay, let's thank the speaker again.